Hey everyone, and welcome to our lesson on Stereocenter nomenclature. We're going to be going over the Cahn-Ingold-Prelog system today, as well as going over the differences between enantiomers and diastereomers in order to better understand them. So the first thing we're going to kind of look at here is the typical naming system for organic molecules. So here I have S plus methamphetamine. And you'll see this as a very common way of naming molecules, especially in organic chemistry. So let's kind of dissect this for a bit and take a look at this S here. So this S actually refers to the absolute configuration of the molecule, which we'll be talking about today. This plus written here refers to the optical rotation of the molecule, or its optical activity. So if you recall from the stereoisomer video, we talked about the rotation of plane polarized light. And so a plus here means that it rotates the light in a dextrorotatory or clockwise direction. So you'll see this a lot in organic chemistry as well. And then this last part here is simply the name of the molecule that we have, which is methamphetamine. So to dive into the absolute configuration further, we're going to be talking about the Cahn-Ingold-Prelog priority rules today. So this assigns the absolute configuration of the chiral carbon. So to apply these rules, the first thing you need to do is identify what the stereocenter or chiral carbon is. So let's take a look at this molecule here on the right. You can tell kind of right away that the chiral carbon is this one right here, as you can see with the 4 different attachments to it. The next thing we need to do is identify the atomic number of the attachments to each of the attachments to the carbon. So let's take a look over here and maybe look at what's directly attached to the carbon here. So the oxygen atomic number is 8. I'm simply looking at a periodic table for these values, 6 and 6 here. Okay, and then a hydrogen is of course A1. So now that we've assigned the atomic numbers to the things that are attached to the molecule, we need to prioritize and rank them. So the higher the atomic number, the higher the priority it gets. So looking at, I'm going to change my pen color here so we can kind of see this a little bit better. So looking at this, you'll see that the highest priority one that's attached to the carbon is this oxygen here. So this will actually be assigned a 1 for number 1 priority. Next, now we have 2 carbons that we need to consider, and they're both equally, of course, 6 as their atomic number since they are the same element. In this case, usually you will look at the molecule or the next atom that's attached to the one that's directly attached to the carbon, the chiral carbon. So we look at the molecule that's next attached to this one that's competing with each other. So for this case, the oxygen is the next one, and the atomic number of oxygen is of course 8. Whereas the next molecule, the next atom that's attached to this carbon is a hydrogen whose atomic number is 1. So between oxygen and hydrogen, oxygen has a higher atomic number and thus gets a higher priority between these two. So we assign the second priority to this one and the third priority to this attachment. That being said, the last priority goes to the hydrogen, and it's almost always the last priority. But not necessarily always, but it's a good kind of trick for you to consider when you're doing the Cahn-Ingold-Prelog priority rules. So now that we have the priority assignments, let's take a look at the direction of this configuration. And that direction, whether it's clockwise or counterclockwise, will help us determine whether or not we have an R or an S configuration. So I'm going to change my pen back to this blue here. And if you have a clockwise assignment of priorities, you give the molecule an R configuration. If you have a counterclockwise arrangement of the attachments, then you give it an S configuration. So let's look back at our molecule here. And the first thing we want to do is make sure that our lowest priority group is in the back, or pointing away from you into the page. So in this case, our lowest priority group is this hydrogen, and it is indeed pointing back into the page as indicated by these dashed lines. So we're good to go there, and you'll see why this is important to do later on. So looking at this, we really just need to focus on the 1, 2, and the 3 here. And if you kind of look at it, you can see that it goes 1, 2, 3, 4. So if you were to imagine how this molecule were to be, if it was facing you directly, these hydrogens pointing in the back, you'll see it actually goes in this counterclockwise direction. So we're going to give this molecule an S configuration. So there we go. So let's take a look at another example here. I've basically filled in the blanks that we mentioned in the previous slide here, so you can kind of see what the steps are. But let's take a look at our next molecule. This is actually valine, which is an amino acid that will come up later on in organic chemistry, or maybe in your biochem class if you're in biochem right now. But let's first start by identifying what the chiral carbon is. So I can see it right here already. And we're going to basically go through and identify what the atomic numbers are for each of the attachments to it. And I'm not going to write the atomic numbers in on the slide necessarily, but just know that you can always refer to that periodic table and take a look at what their atomic numbers are if you need to verify something. So I'm going to take a look at the things that are directly attached to this chiral carbon first. So let's take a look at this one. So we have nitrogen here, a carbon here, and I'm going to draw this in, a hydrogen here. So don't forget that there's a hydrogen there. So out of the nitrogen, hydrogen, carbon, and carbon, I know that nitrogen has the highest atomic number at around 7, so this will be assigned our number 1 priority. The next thing we need to consider is this carbon and this carbon. So here again we have 2 carbons that are equally okay in terms of their atomic numbers in prioritizing. So because of that, we need to look at the attachments that are continuing on down the chain of things attached to the carbon here. So this carbon is attached to 2 carbons, this one and this one, whereas this carbon is attached to oxygens. So because of that, oxygen does have a higher atomic number than these carbons here, so we're going to assign the second highest priority to this whole attachment here. So then that provides third priority to this attachment, and then our last priority goes to this hydrogen right here. So if we were to imagine this molecule 3D form with this hydrogen pointing into the back of pointing away from you into the page, we would see that there is this counterclockwise rotation. So here we have, again, an S absolute configuration. And this hydrogen is, of course, pointing to the back, so we have our lowest priority group in the back, so that works. So something important to note is you can kind of imagine how, in the case of a double bond, it's almost as if the atom is attached to 2 as opposed to like 1 oxygen. So what I mean by that is, just take a look at this molecule. This is carbone. We're going to start by doing our priority rules as per usual. So we have our chiral carbon here, we have a carbon here, a carbon here, and a carbon here, and we have a hydrogen coming out, and this is going to be a wedged hydrogen since this is going into the back there. So let's take a look at this molecule right now, and we can see that this carbon, and this carbon will probably, one of these 3 will be our top priorities. So looking at this carbon, and this carbon, we say that this one will be the next priority because this carbon here is attached to 3 carbons, if you think of it that way. So you see this double bond here. It's almost as if this carbon is attached to 2 carbons here and 1 carbon here. Of course it's not, but this is a good way to think of it when you're doing the priority rules. So our first priority goes to this carbon here. Then we're going to look at this carbon and this carbon now. So again, we have a carbon here attached to a hydrogen, a carbon. This one is attached to a hydrogen and a carbon, so they're still equal, meaning we're going to go to the next thing that's attached to it. So now we're on this carbon here and this carbon here, comparing these 2. So this carbon is attached to 2 carbons here and a hydrogen here, whereas this one is attached to 2 oxygens and 1 carbon here. So since oxygen has a higher atomic number, we're going to assign the second highest priority to this attachment, third to this attachment here, and fourth to the hydrogens here that's coming out. So with that being said, we're going to draw our directions as per usual. So we see 1, 2, 3, go like that. We see that as counterclockwise, but our lowest priority group is coming out of the page. Unfortunately, it's not pointing away from you. So in this case, you can't automatically assign an S configuration even though it's going counterclockwise. So this is an important step to remember. Whenever your lowest priority group is pointing into the front instead of the back, you still assign all the configurations like normal, doing your rankings and prioritizing. However, whatever you get, you do the opposite. So here we got an S configuration, but we're actually going to assign it as R minus carbon because it's as if we flipped it over and put the hydrogen in front instead of having it in the back. So just do the opposite of what you get when you do your prioritizing as per usual. Okay, and just something to keep in mind is that the R and the S and the plus and the minus, which is from the optical activities, for the rotations of light, plane polarized light, are actually different. So I know they both refer to clockwise and counterclockwise directions, but they are separate from each other. So R does not necessarily always go with minus or plus, and S does not always necessarily go with a minus or a plus either. They are separate concepts.